Section 17.3, I'm going to discuss systems that undergo oscillation. To start with, let's consider a mass that's connected to an ideal spring. If we move the mass away from its equilibrium position, then the spring is going to stretch or compress some distance x. Well, if it's stretched, then there's going to be a force that causes the mass to accelerate, and that force is going to be caused by the spring, and the spring will always exert a force opposite the stretch. So if x is positive, the force is negative. If the x is negative, the force is positive. And so we have this situation where the acceleration of the mass depends on its position. And the position and acceleration are always opposite in direction. And this is the pattern where acceleration is proportional and opposite in direction to the position that will cause a system to undergo simple harmonic oscillation. That word harmonic just refers to a math thing. It's not a real important idea. It's the simplest kind of oscillatory motion, where it goes back and forth in a regular amount of time. And we can look at some of the features of a spring mass system. That's what this is called. It's a mass connected to a spring. We can first look at what's known as amplitude. Amplitude is the maximum compression or stretch. And it goes back and forth between plus A and negative A, back and forth the same distance each time. And there's a cycle that spring mass system goes through. There are 4 main points that some special things happen. So the first point is where we're at maximum stretch, where it's at a positive amplitude. And notice that the force is always back towards the equilibrium position, x equals 0. And if we look at the position, velocity, acceleration, and force, we can look to see if they are maximums, zeros. Are they positive? Are they negative? And at this point, the position is a positive maximum. The velocity at endpoints are going to be 0 because those are turning points. Prior to getting to that endpoint, it's going to be moving to the right, and then it's going to be moving to the left. So at that point, it's going through a turning point and will have 0 velocity. Now, the force at this point is going to be a maximum. This is going to be a negative maximum value, because this is the furthest that it stretches, and so the spring is going to be exerting its maximum amount of force, but in the negative direction. And since acceleration depends on force, this will also be a negative maximum at that position. Sometime later, the mass will have moved back to its equilibrium position. And so now it's here. And at this position, the position is 0. And since force depends on position, the force will also be 0. And if the force is 0, the acceleration is 0 while it's going through its midpoint. But at this point, it's got a maximum speed and it's moving in the negative direction. And that's because at the endpoint, it's got all elastic potential energy. And it's a maximum at that point. No kinetic energy. That elastic potential energy gets converted into kinetic energy where it is a maximum, and when it has maximum kinetic energy, it has maximum speed. So later, it then moves all the way to a max compression. And at max compression, now it's got a position that is a negative maximum, which means that the force will be a positive maximum. And that causes a maximum positive acceleration. And again, at the endpoints, it's undergoing a turning point, and so the velocity is 0 at that position. And then we have one more point. Now it's going back through its equilibrium position, but now it's undergoing, it's going in the opposite direction. So at this point, it now has 0 position, 0 force, 0 acceleration, but now it's got a positive maximum position. And after that, then it, of course, goes back to its original position, and then the cycle repeats itself over and over and over. And those are the important positions that we have to consider in order to calculate some important values. Now, the mass will complete and then repeat that cycle in a certain amount of time, and that certain amount of time is called a period. And since it's a special amount of time, we give it a capital letter T. And that period depends on the properties of the system. It depends on the mass, m, and the spring constant, k. And you can see here we have TSM, that stands for the period of a spring mass system. In the next section, we're going to look at a pendulum, and pendulums also have a period, so the pendulum will be called T sub P. I use an SM to indicate this is a spring mass system. When we talk about period, we can also talk about frequency. Frequency is how many cycles occur per some amount of time, and frequency is just the reciprocal of period. And we have standard units for this of cycles per second, and a cycle per second has a nickname. It's called a hertz. Okay, in this example, we have a cart with a mass of 4 kilograms attached to a spring with an equilibrium length of 25 centimeters and a spring constant of 357 newtons per meter. Student pushes the cart to compress the spring to a length of 10 centimeters and then releases it from rest. Part A wants us to determine the period of oscillation. So calculating this is a straightforward application of the formula. The period of a spring mass system is given by 2 pi times the square root of the mass over the spring constant. And we have the mass and the spring constant, so we're just going to plug and chug. So the mass is given as 4. The value for K is given as 357. Take the square root of it, and that gives us the period. And the period is going to work out to be 0.67 seconds. In part B, it wants to know the frequency of oscillation. So frequency is just the inverse or reciprocal of the period. So I can take 1 over the period, and that gives me 1.5 cycles per second, or 1.5 hertz. Part C wants us to calculate how many oscillations would happen in 1 minute. So if we have 1.5 cycles per second, if we want to know how many cycles per minute, every 1 minute is 60 seconds. So we're going to take the 1.5, multiply it by 60, and that's going to give us 90 cycles per minute. And then last, we're going to look at how far the cart travels in 1 period. So if we think about it being starting from the compression, it's then going to move a distance A, that's the amplitude, to its equilibrium position. It continues for another A till it hits the end point here, where it turns around and moves back to its equilibrium position, moving a distance A, and then it continues moving all the way back to where it started, another distance A. So the total distance that the cart is going to move is going to be 4 times the amplitude in 1 period, and it has an amplitude of 10 centimeters. It's got a equilibrium length of 25, and it's got a compressed length of 15, so that means the actual compression distance is 10, and 4 times 10 centimeters gives us 40 centimeters. So in one cycle, the cart moves a grand total of 40 centimeters. In this example, we're dealing with the same exact situation as the last one. It's just asking us a few different questions about the same situation. Part A wants us to find the maximum acceleration experienced by the cart. So, acceleration depends on the force. The spring is what's exerting the net force on the cart, and the value of the spring force is given by K times X. We know the value of K is 357 newtons per meter, and the value of X when it's a maximum, aka the amplitude, is going to be the difference between the equilibrium length and the compressed length, which is 15 centimeters. And that difference gives us 10 centimeters or 0.10 meters. It's really important that we're in meters so that the units of meters will cancel out. And then we can divide by the mass, which is given as 4. And this gives us a value of 143 meters per second squared. Where does this occur? Well, this is going to occur when the stretch or the compression is a maximum, and that happens at the end points in the motion. Now, for part C wants us to find how much energy the system has. Well, at the end points, it's not moving, and all the energy then is elastic. And we can calculate elastic potential energy with 1/2 kx squared. We were given the value of K, that's 357. We were given the value of the max stretch and max compression, that's 0.1. And so the total energy available in the system is 1.79 joules. Part D wants us to find the maximum speed of the cart. Well, that's going to happen at its equilibrium point, at its equilibrium position. And at the equilibrium position, all of that elastic potential energy that is stored up in the spring at the endpoints gets converted into kinetic energy. So that elastic potential energy that I know is 1.79, that will end up being the kinetic energy, which is given as 1/2 mv squared. We're given the value of the mass, and if we solve for the speed, we get 0.95 meters per second.